had to put.
Yes, we can.
Okay, does it move back and forth?
It does.
Cool. Okay, so hi, I'm Leo Werneck. I'm a postdoc at West Virginia University, and today I'll be talking to you about IllinoisGRMHD. Oops. Okay. So I will start my talk by providing a brief overview of the code, and then I'll jump straight into the latest developments that we have done and improvements that we have done to the code, which include tabulated equation of state support, the ability to evolve the electron fraction as well as the entropy, the latest developments that we have done to the conservative to primitive infrastructure of the code. And then I'll discuss our latest results. And I'll end the talk by providing a brief summary and an overview of what we plan to do in the future. So IllinoisGRMHD is a rewrite of the original GRMHD code of the Illinois Numerical Relativity Group. It agrees with the original code to round off error level while being twice as fast and containing far fewer lines of code. It provides GRMHD for dynamical spacetimes, including neutron stars, binary neutron stars, both of this with and without magnetic fields, as well as black hole accretion disks and many other scenarios. It's completely open sourced and available as part of the Einstein Toolkit. And it has been documented in pedagogical Jupyter notebooks, which are available at nervybless.net. You can also take a look at my previous TCAN workshop talk where I discussed this documentation in a bit more detail. So originally, IllinoisGRMHD had hybrid equation of state support with a code simple polytropic base. And we had extended that last year to also support piecewise polytropic equations of state. And now we have extended that support even further to also be able to handle fully tabulated EOSs. We have also added the electron fraction and entropy evolution, and we have done a major overhaul to the conservative to primitive infrastructure, which is specially tailored to minimize spurious heating of the neutron stars when using tabulated equations of state, which we will discuss in more details later. So tabulated equations of state the usage of those are motivated by the fact that they provide the most realistic descriptions of neutron stars that we have available to date. So the tables usually provide hydro quantities in terms such as the pressure or the entropy or the specific internal energy in terms of density, electron fraction, and temperature, meaning that the tables are typically 3D. Our implementation is built from the open source and freely available Zero-Mounting infrastructure by O'Connor and Ott, which is available in stellarcollapse.org. And we integrate the equation of state support with the Einstein Toolkit through an optimized version of the EOS Omni Thorn that we have developed over the past year. When using tabulated equations of state, we typically need to recover the temperature during the conservative to primitive routine. Now, recovering the temperature using the existing infrastructure is possible. Typically, you provide the specific internal energy or the pressure, and there's a table inversion algorithm that will determine the temperature for you. However, what we have found is that in regions of the table which are typical for neutron stars, that is high density neutron rich regions, the dependence of the pressure and the specific internal energy on the temperature is very, very weak. And that means that if we have small errors in pressure or specific internal energy, this can be greatly amplified and result in very large temperature errors, causing very large heating of these stars. So one way we found to fix these problems is to, instead of using the pressure or the specific internal energy, we use the entropy instead. This has greatly minimized, it has greatly mitigated the issues that we were seeing, although maybe there is some room for improvement by using the latest counterprim routines and schemes that have been suggested in the literature. The new evolution equations used by our code look like this. The first three are the standard GRMHD equations which were used, which are conservation of baryon number, conservation of energy momentum, and the homogeneous Maxwell's equations. And now we have also included the conservation of lepton number and conservation of entropy. The first of the new equations in particular introduces the electron fraction, which is what we need for tabulated equations of state. So these equations are typically written in conserved form, meaning that we evolved a vector of conserved variables, such as the conserved density, conserved energy, conserved momenta, etc. But we are ultimately interested in computing the primitive variables, such as the baryonic density, the temperature, the pressure, the velocities, etc. Now, going from P, the primitive variables, to C, the conserved variables, is trivial because we have analytic expressions that relate the two quantities as well as the metric quantities. But going from C to P is very complicated, and it can range from solving a single nonlinear expression to multiple nonlinear expressions, and often requires a finding algorithm. Now, in IllinoisGRMHD, we do not keep track of the primitive variables in the previous time level. That means that we do not have good guesses for our primitives at the current time level. And therefore, routines that require a Newton-Raphson solver, which are typically 2D routines or 3D routines, which require the solution of multiple. Sorry? No. Okay. So which require the solution of multiple nonlinear equations are typically not good. We have tried to use those in our code, but they are not very reliable because we cannot provide good guesses. Luckily, there has been some good progress on this. There's a very, very neat infrastructure that is open source provided by Siegel et al., which contains many options for different recovery schemes, and in particular, a couple of effective 1D routines due to Palenzuela et al. And to Newman and Hamlin are very, very robust, even when we have very poor guesses for the initial primitives. And so we're using a modified version of these routines that can use the entropy instead of the specific internal energy during the recovery scheme. And this is a result from a simple test that we have done with our code that tests the accuracy of the recovery schemes. So what we do here is we consider flat space, and we set the components of the velocity and magnetic fields randomly, subject to the constraints that both the Lorentz factor and the magnetic pressure I kept fixed. We then discretize both the density and temperature evenly in a log scale, and we compute the conservative from the known primitives, and then we attempt a recovery. So it's a primitive to conservative to primitive test. And then we are able to compare the primitives that go in with the primitives that go out. And what we're showing here are the comparison between the relative errors between these primitives, and the results are pretty good. So while the success rate of that test is 100%, we didn't find any failure there. These failures do occur during a binary neutron star evolution. And of course, these are constantly monitored. And if a failure occurs inside a neutron star, that is, that's something that we would never allow, and the run is terminated immediately. However, they do happen in the artificial atmosphere of the code. And so we have found ways to handle those that are more, they're more in the style of what IllinoisGRMHD already does. So basically what we do once we have a failure is we flag that point, and we attempt additional recoveries on that point by considering the average of the conserved variables at that point and the neighbors for which a recovery has succeeded. We do that up to 4 times, increasing the weight we give to the neighbors as shown here in the equation. And if after all that we still have not been able to recover the prims, which is something that happens very rarely, then what we will do is simply reset the primitives to their atmospheric values and their velocities to 0. So with all this in mind, with all this new infrastructure in mind, I'm going to be showing you now results from our latest simulations. This is a binary neutron star that has 2 equal masses neutron stars of about 1.39 solar masses each. The initial separation is 45 kilometers. And this is a magnetized run with the ratio of the magnetic pressure and the fluid pressure initially set to 10 to the minus 4, which corresponds to a magnetic field of roughly 10 to the 15 Gauss. We used the O'Connor and Knott LS220 tabulated EOS. And the initial data for this simulation was provided by Tamayi Gupta using the Lorraine code. The simulation was also run in Frontera. So I'm going to be showing you two panels here, which will be evolving simultaneously. On the left, you'll be able to see the baryonic density of the fluid in a log scale. And on the right, you'll be able to see the temperature. So if I play the movie and I let it run for the first 3 milliseconds or so, you see that there is some heating inside the star. So although we have mitigated the problem, it is not completely gone. But this is a significant improvement over what we had before we started using the entropy equation. So before that, the temperature inside the neutron stars could get up to 20 MeV very quickly. And it would be so, it would never stop increasing, essentially. There was definitely something odd going on in there. But with this, you will see that the temperatures inside the neutron stars never get above the 5 MeV threshold or so. So if I keep them going, oh yeah, there is some heating on the surface of the star, but this is less worrisome. So at about 12 milliseconds, the stars touch. They will form a hypermassive neutron star with a mass well above the stable threshold limit for this tabulated US. And so shortly after that, at about 15 milliseconds, the star will collapse into a black hole. And at that point, the movie will start displaying the apparent horizon of the black hole, so it should be pretty easy to spot it. And now the evolution simply continues until about 26 milliseconds, which is where we're going to stop the movie. So there's very little drift, which is expected for an equal mass binary, so that's good for us. And this black hole contains about 90% of the initial ADM mass. So that gives you an idea of how the mass of the ejectas, of the remnant disk as well. And over here in the bottom panel, I also showed the dominant mode of the gravitational wave signal extracted at a radius of about 440 kilometers. And we can see that it looks pretty clean. There's no sign of any issues in the run. Oops. Okay, so to summarize, IllinoisGRMHD has been updated to support tabulated US. We have upgraded the counterprim infrastructure. We have added support for both the electron fraction and entropy evolution. And I would suggest you catch Fede Armengol's talk on Thursday for more information on how the run is going to proceed from now and the handoff that we're going to do to HARM3D. And adding neutrino physics to IllinoisGRMHD is also something we are doing right now. So keep tuned for that. So thank you.
Thank you. Let's thank the speaker, and we have plenty of questions coming up. So I think the first one I have here is from Cole Miller.
Thank you for the presentation. In terms of the entropy conservation that you are imposing, what about when there are shocks, as you might expect when the neutron stars actually collide?
Yeah, so we do have, so we do apply to that the same PPM procedures that we do for the other primitive variables, but our evolution is just that. We simply treat it as an additional thermodynamic quantity. We had done some experiments with that in the case of hybrid DOS before, and we found that it did improve based on work on that has been done on HARM3D with HARM3D in the past. And so that's the only treatment that we are using right now. I actually was pointed out in the past that there may be room for improvement there, but for now, we're just using this simple evolution by simply subjecting it to the same ppm treatment that the other hydro quantities that are evolved are subject to.
Okay, so this means you actually do not generate entropy when there are shocks. So, but this is improved enough in terms of the pre-merger evolution that it's a good bargain. Is that right?
Yes.
Okay, thank you.
Okay, Wolfgang.
Yeah, I had similar comments. So, I mean, if the reason people evolve the energy density is to get shocks, right? In particular, also the shock speed. So this might break, but it might still be a nice thing to have for the in spiral. My other comment is that this increase in temperature when evolving energy density instead of entropy density, this seemed a bit large. So I have simulations doing also without any entropy evolution, and 5 MeV seems normal to me because, as you said, the temperature is very degenerate at these low temperatures. But 20 MeV, this sounds odd to me. It sounds like there might be wrong something else. So it might not be a improvement in the of using the entropy, but just accidentally fixing some bug. Of course, I might be wrong here. This is just a feeling.
Yeah, so the reason why, so I agree, we actually tried to fix the code directly because we suspected there was something wrong. But when we started experimenting with simple tests where we perturbed the specific internal energy to something much smaller than what we expect to see during an actual evolution, the errors in temperature increased so rapidly that we figured there was going to be no hope of actually getting reasonable heat up by using the specific internal energy or the pressure. But maybe we could do that by fixing the way that the tables are being interpolated or the temperature is being covered from the table. We have actually some fixes for that, but those did not seem to improve our results significantly.
Okay, Eric, you have a question?
I have a question regarding the table with the equation of state. People often spend a lot of time inverting the table and looking for a particular energy and similar. Has anybody tried inverting the table ahead of time, storing it differently? And I'm also thinking about doing this on a GPU, and then a smaller table would be more convenient. So would it make sense to use higher order interpolation with fewer data points?
I have not worked with that, but I can see some benefits for working with smaller tables, but yeah, I don't know. I don't have much experience with the tables themselves.
This might be a question for Tamayi Gupta tomorrow.
I will ask again, but thank you. But so far what I hear is good. That there's not an obviously bad idea to do that. Thank you.
Okay, thank you, Leo. And the last